afternoon, everyone. Welcome to this, the last lecture of the last mini school of the year into the introduction to Haskell. Yes, and today Yorick and Brink will try, I assume that not bring this story to an end, because as instead there is no end to this story, but at least to bring it to some point from which we can go by ourselves. So, and the first for the first half, Yorick will talk, and afterwards Brink will take over from there. Yorick, so yours.
Great, thank you, and welcome back to everyone. Thank you for your persistence coming each week. So let me just share the screen. All right, so hopefully that is visible now.
Yeah, we can see your screen.
Great, I'll just move that over there. So I thought what we'll do today is we'll just build out a little bit on what we did last time, but also looking at how we can define our own type classes. And we'll do that via polynomials, and we'll build up sort of a implementation or a reflection of some of the mathematical structure, and hopefully it will lead to something that mirrors the way that we think about it to some extent. I'll also show some pitfalls, because when we get to the end, we'll see there are ways that you can think about it that seem pretty natural, but aren't necessarily what Haskell is able to do, or is not within the prescription of the languages. So firstly, we're going to look at Autodiff again. The only thing that I've changed here is I'm now not looking at double anymore. I'm looking at an arbitrary type A. So a map from A to A for the function, and a map from A to A for the derivative. And the reason I want to do this is, for example, to work with polynomials and allow differentiation in rings and so on. So that's the idea. The only thing that changes in the Autodiff data type is that now I have to, instead of just straight going with values I and 0, I now need to say that I'm getting it from an integer. And because I have num A, so if A is a numeric type, then I can implement these features in Autodiff. So taking the fact that it's a numeric type, I can get its numeric or its value for 0. So that's the only differences that we have in Autodiff. And then what we're going to do is build up the idea of polynomials and eventually bring them back and use them in this Autodiff type. All right, so let's look first, what is a polynomial? A polynomial is going to be just one simple thing, and that is a polynomial over A is actually just some, well, it's a constructor polynomial, but it's a list of A's. So that is going to be our coefficient, starting from the coefficient for x to the power 0. I'm assuming everyone knows what a polynomial is, so let's just write it in case. It's things like 1 plus 3x squared plus 5x to the 7, something like that. So what we want to do is store the coefficient. So 1, 3, 5, but we'll do it as 1 plus 0x plus, what was next, squared, plus 0x cubed, plus 0x to the 4. Probably I won't type everything out, and so on. And 5x to the 7. So that's how we're going to represent it, just as a list. And let me just write that out. It will be 1, 3, 0, 0, and then I'm not going to count them, but anyway, up to 5. So that's what that will be our polynomial. Now, the first thing I'm going to do is find a way to show it. Of course, I could just show the list, but to make it a little bit more appealing, although not completely, we'll show a polynomial. So we need equality on A for being able to compare values of A. We need that A is a numeric type so that we can, I don't remember what the numeric is for. The numeric type is going to be later in the polynomial. And then we need to be able to show the coefficients. So the way that we do it is we combine terms using the concatenation operator. So we take two terms, x and y, we combine them by concatenating them with a plus in between. And this concatenation we use as part of the fold. So we fold over all the terms, starting with an empty string, adding all the plus terms. It's got a little bit ugly, so it could be fixed a little bit better, but I'll leave that as an exercise if you want to play with it. What are the terms? Terms are the way that we show the term, so the string value of the term, and applied to zip and A0 onwards. So maybe I should just show you what zip does. So if I take zip of a list 1, 2, and 3, and I zip it with 1, 2, 3, without the comma, it will create a list of pairs, 1, 1, 2, 2, 3, 3. I'm cheating a little bit because I can do infinite lists. So I can take the infinite list from 1 onwards and have 1, 1, 2, 2, 3, 3. So I combine the coefficients with the powers in pairs by zipping them. The first coefficient is power 0, the second coefficient power 1, and so on. So each of these represents a term, and to show it, I take the pair and I put brackets around the coefficient, show the coefficient, concatenation again, and x to the power, and then show the exponent. I do have one small thing here to fix. I do allow for empty lists, which means a 0 polynomial. And so if I get an empty string, then I just write it as a 0. Otherwise, it's just what it should be. So let's have a look quickly what that looks like. Did I load already? So if I say B is a polynomial with coefficients 1, 0, 0, -1, 2, something like that. Oops, with an equals. And I show it, then it will show in this way. It's plus, and there you can see a little bit of the ugliness coming in. +1, first coefficient x to the power 0, 0x to the power 1, and so on, up until x to the power 4. So we can show polynomials. This is actually probably the most difficult part. Let's just switch here. The actual implementation is very short. So what we're going to do is we're going to assume that we have a numeric data type underlying. And if we add a polynomial to another polynomial and it's the empty polynomial that's like 0, then we just take the second polynomial. If we add a polynomial to the empty polynomial, then we get that same polynomial again. Otherwise, what we need to do is add their first terms. So we add a plus b, and then we must find out what the rest of the polynomial is. How is that found? By adding the rest of the terms. The rest of the terms, what we do is we take the list of the polynomial of a's added to the polynomial of b's. So actually what I did is I shifted everything down. I took the x squareds and made them x's, and x cubed and made them x squareds, and so on, add them in that way, and then I add onto the front the coefficient term. And so list of is just a way to pull out this list. Right, so that's a very simple implementation of addition. We also have multiplication, and then a few things here. Most of them are not implemented. Multiplication will also be pretty simple. If I multiply with an empty polynomial, I get the empty polynomial. If I multiply by a polynomial with a constant term, and then the remaining terms, so those are the coefficients, times another polynomial, all that I want to do is multiply through. So I map multiplication with a along all the coefficients. So that's, for example, if I say map 3 times on 1 through 5, it will multiply each term by 3. So that does the multiplication across all the coefficients for the first term. And I add to that, and so here's a little trick. All that I need to do now is every higher order term is at least x or x squared or x cubed. So take it down 1, so x squared again becomes x, and so on. Do the multiplication and then multiply by x again. How do I multiply by x? I just put a 0 on the front. So we can see this. If I have b is this polynomial again, and I show b, then you'll see it's 1 x squared, 0x to the power 1, so on up to x to the power 4. And if I just put a 0 in front of that, then it's multiplying by x. So that's how we do the multiplication. And this is all very short. This is, I was saying just before we started, the sort of the briefest implementation that I can think of, but it's certainly not the best way of multiplying. But it does the job for, at least for this example. To negate a polynomial, I just negate all the coefficients, and absolute value and sign I will not worry about. And lastly, I will convert from an integer to a polynomial just by putting the integer in the constant term. So this allows us to do things as follows. So x is the polynomial uh, 0, 1. So if I look at how it's represented, it's 0x squared, 0x to the power 0 plus 1x to the power 1. So I can now make polynomials such as x cubed plus 3x, and it will do the algebra in the usual way. All right. There is an immediate way to implement the functor. So we'll have that polynomial is an instance of functor. How do we map? Given any function on A, so if we've got polynomials over A, then I can create a map on the polynomials by applying that map to the coefficients. So this is, I fought with this a little bit. There are other functors that we could come up with, but this is the one that fits in with the Haskell idea of functor. The rest of any other idea that you might have for functor would be just implemented as a function. So you cannot do that in terms of classes and instances. All right, so are there any questions so far?
Do you perhaps have sort of a sample use case for the fact that polynomial is now an instance of the functor type clause?
So immediately as rings, this corresponds to ring homomorphisms. So when you do this map, what is a ring homomorphism going to do? It's going to apply to the coefficients into terms x. I haven't, of course, so you still have to do the substitution of x, but so that would be the one idea. So every ring homomorphism induces a homomorphism on polynomials. And then with one extra step, actually an evaluation would also then give you the desired result given the function f from one type to another. I should just mention one thing. I can do bizarre things. So this functor makes perfect sense, but not everything makes perfect sense. Let me just write polynomial A, B, C. So my coefficients are now strings. Did I do that? So let me assign that to, let's call it P. So P is a polynomial, but the first thing that we notice is that I cannot even show it. And the reason is because to show polynomials, I need them to be over a numeric type. I also cannot add, I cannot multiply, because even if I tried to take P times P, it's not a numeric type, so it cannot do these operations. So the idea of a polynomial is the fact that it has a numeric implementation together with the declaration of the type. Sorry,
but I guess
I went all over the show. Yeah.
I guess that makes sense, since if you want to multiply or add your polynomials, you need to multiply and add the coefficients. So that's why you need the A or the coefficients to be an instance of the num type clause. Otherwise, yes, you don't know you can add and multiply them. Yes,
that's right. And so in actual fact, what I would like to do is be able to do this over a different setting. So maybe string isn't an appropriate numeric type, but maybe you could still do something sensible with polynomials. And so what we can look at is maybe the implementation of rings. So if I can make a ring out of my strings, and we should be able to do some of that, then I can make a polynomial over the structure and still do sensible things. So that's what we're going to do, is try work from this idea of polynomial to one where we only work over rings. So let's start off with the idea of a unital ring. So I'm going to use a unital ring because it makes some things easier. We don't need a unital ring, but then we complicate some of the implementation later. A ring is a structure which is equipped with addition and multiplication and additive identity. And here you'll notice I've put comments that it should be associative and distributive, and the 0 should be the additive identity, but there is nothing enforced in Haskell to make this true. So it's my job as the implementer to make sure that I obey these axioms for ring. It has negation for the additive inverse and minus. And here I'd just like to point out, normally we would write this as plus. But we start to run into problems with this because plus already exists in another class. So let's just go back. So plus is already in another class. So here, all these names, I hope I've done it correctly, but it should all be unique. So it doesn't appear anywhere in the prelude. I've added 2 default implementations. So minus can be defined in terms of negation if negation is provided, and negation can be provided in terms of minus if minus is provided. So this is when we see normally that we've got num A gives us that polynomial is a numeric type. This is the same idea. So we would normally have class num A where and then describe these structures. And then from this, I can also talk about commutative rings, but here this is a declaration basically. I need to start with a ring over A, and that can provide a commutative ring over A. And here, for example, I will just skip a few steps. The integers form a commutative ring. So what I do is I first declare them as a ring, and then I say that integer is an instance of C ring, and I don't do anything further. It's just Haskell will believe me that it is a commutative ring. So commutative ring is where multiplication is commutative. I should have added here, of course, addition is commutative. Right, so that's my setup for rings. And now integers we can see is a ring, just where plus is the usual plus, times, and so on. And so we've got our usual ring structure. And now any operation on rings we can describe and then also do the same for integers. So now we can go back to polynomials and start talking about them in terms of rings.
I just had a quick check, and I see there is on Hackage I had a check, and in the algebra module there is a ring type class. Yes, there is. You're right. So we should maybe mention it. Will that be in the resources later, Brink? I haven't added it, but I guess I could. But you can also just mention, people can just look on Hackage, and so it's algebra.ring. Algebra.ring. Yeah. So similarly, there's yes. There you have semigroups and monoids. Yes. So there are a lot of these algebraic structures already implemented in the as modules that you can load. And so what we're doing is basically probably providing a poor implementation here, but just to see how you would do it. So thanks, Brink. The libraries are extensive. You can find a lot of firstly, structures from mathematics, but many structures in general that you can use. So this is a very useful resource. But mostly what we're doing here has already been done there. So auto differentiation is already there. Rings are already there. Most of what I'm implementing here is already done. So it's more just an illustration of how you could approach it. All right, so now we've got our ring over integers and our commutative ring over integers. So it's same ring, of course. We can look at how we can make polynomials over a ring. Well, one of the things I'm going to do is I'm going to be lazy, and I'll leave this as an exercise if anyone wants to play with it. We'll put the code up after the course. Here I'm saying that if I've got a commutative ring A, then I can make a polynomial over A
and that will be a ring. And moreover, it will be a commutative ring. So there's the definition for the commutative ring. And the operations are going to be, again, just plus times. The 0 is going to be the empty polynomial. 1 is going to be the polynomial with 1 in the coefficient. This 1 comes from the fact that we've got a C ring, which is a ring, and so on. The lazy part is that I'm leaning all on plus and times and minus as I've defined it over here, so that I can do it in a relatively natural notation. But otherwise, we would use this plus times 0 and minus and so on to do all the operations. So, but from here, I think I'm going to try use all the ring operations directly. So another thing that we can do is we can extend it to be a ring with differentiation, which I've called the D ring here, which must provide a map which takes type A and gives you type A again. So in our case, that will be polynomial over something and give us another polynomial, and that would be the derivative. So let's see, do we have an implementation? Here's an implementation. If I take a polynomial with a list, the first coefficient A and the rest of the coefficient A's, then what I can do is I can create the derivative terms by, again, zipping. Notice here we're starting with the A's, so we just dropped the A, we differentiate it out, and then I'm going to associate with it the powers. So I'm zipping A's. The first power is 1, the second is 2, and so on. And what is a diff term? It takes Cn and it takes the coefficient and it multiplies it with the power, so from integer of n. And here again, I'm leaning on num, but we could extend our implementation a little bit so that it doesn't need num, but rather just rings, or ring with the ability to take from an integer and embed it in the ring. Right, so that's pretty much the whole story. Now, polynomial is a commutative ring and a ring with differentiation, so we can use it to create an auto differentiation instance. But we cannot do it in the sense of functors or something like that, at least not in terms of instances. So we'll have to do a little bit of work in terms of functions. So let's skip ahead first and look at how we would do it. I've chosen a very bad name, make auto differentiation from a polynomial P. What I do is I have a function here, which we'll go through in a moment, which is to make a function from P and also make a function from the differentiation of P or derivative of P. How do we make a function? Well, we have to take a polynomial and given an argument, it should produce an argument. So the way to read this, it's right associative. So given a polynomial, it produces a function from A to A. We don't need the brackets on the right because of the associativity. So what we can do is we can basically describe, if I insert x into the polynomial, what will I get? So all we have to do is calculate each of the terms. So again, I zip the coefficients with the powers. That makes the pairs coefficient with its corresponding power. And so what I'll do is I'll multiply Cn with the power x to the power n. The definition of power is simple. If the power is 0, then I take 1. And if the power is n, then I'll just take, again, n minus 1. Again, there are much better ways perhaps to do this, more efficient, but this is a simple definition. And so what I do is I map all those values, I fold them under addition with 0 as the initial value. And that's the whole story for polynomials. So now we can make these functions. Let's see, have we got B still? So I can say f is the function which I produce from B, and I can take, for example, f of 1. That should be easy to check. So I will have 0 plus 1 plus 0 minus 1 plus 2 should give me 2. So that is correct. And then I can also make an AD from B. I think I'm going to have to reload, because let me just reset because I overwrote F. So now I can take the f part of AD as we did before and apply it to 1. I should also get 2. I can also take the derivative part. We can check it. Let's actually do that. Differentiate B. There's our polynomial. If I apply it at 1, that should be easy again to check. And that should give us 7 as we see there. All right, so maybe just a comment, if I can get the windows. A comment at the end of some things that are possibly confusing if you're coming from the mathematics side. I wanted many times to do the following. If I've got a numeric class, then with all the standard numerical classes that we have in, or data types in Haskell, we can immediately make a ring, and I can just use plus and times and so on. But because ring is a class, so it starts with class ring, not data ring, it doesn't have a constructor, and what has to appear on the right is a constructor with from A. So you cannot write this. It feels very natural, but you cannot do it. And another, I'll just do it for groups. If I want to create a group, another way I could approach it is to say that a group over A is an operation together with an identity and an inverse. So for example, something like this, multiplication with 1. So this would be group over integer or something like that, and quotient. No, not group over integer, group over reals or something like that. So I can make a group this way and represent it. But you will find that if you do this, that some of the ways of writing what we've written is a lot more clumsy or even impossible. You have to make some assumptions in the way that you work with the objects or with the implementation. So this is a natural way to do it, but I've found that in Haskell, this isn't a very comfortable way to do things. Right, so that's pretty much what I wanted to say, just to give you a tour of polynomials and type classes, so how you would implement your own, and a little bit more of computer algebra. So again, I think I'll just pause to see if there's any comments or questions. And if there's any, if you want to see anything, I suppose we can try it quickly.
I don't see any questions from the participants, and it seems like Brink also don't have any comments.
Sure. Okay. So Brink, I don't know if you want to take over from there then and continue on the language side.
Thanks, Eric. So maybe what I'll do is, before I share my screen, I can also put it up elsewhere, but maybe I'll just share you in the chat some links that I think is worth looking at. So the first link, that is just the homepage of Graham Hutton. So sorry, I can, yes.
When you share the link, could you please share it not with the host and panelists, but with everyone?
Yeah, that would be panelists and attendees. Yeah, thanks.
I'll share it quickly if you like.
That's okay, since I'm going to share a few more, so okay. I guess that's better. I hope. Yeah, thanks for pointing that out. So this link is just the Graham Hutton's homepage, and so first of all, I can really recommend his book Programming in Haskell. There's at least the image of the book on his website, but also if you go through his website and you look under teaching, he's got the first and a second functional programming course, and it's all the lectures on YouTube. So I think if you really want to learn Haskell from the ground up, also a little bit in the lazy way, especially since Haskell is lazy, or if you have a student and you want to force the student to learn it, if you go through the lectures of those or just watch the videos while playing along and trying the examples of those videos on YouTube, you'll be a pretty decent Haskell programmer at the end of that. So so that's the first one I want to recommend. And Then the second one, I sort of pointed out to Yorick, and I'm not sure if I should recommend it, but that's sort of the first hit that you get if you start looking for Haskell in category theory, and a lot of people talk about it. And he's also got some lectures, and the author of this particular book on category theory for programmers on YouTube, but I find sort of his lectures on YouTube a little bit on the slow side for my liking. So Yorick said it's okay. He didn't like the C++ code that's also in the book, but especially those of you that know a lot more about category theory than I do, I would like your opinion on that, since I guess I'm also lazy there. I would like somebody to point out to me and say, well, if you're comfortable but you don't really know category theory and you sort of want to combine it nicely, that's what you should read. So yeah, give me some feedback on that. Then sort of a third link that just summarizes many of the type classes you get in Haskell and their algebraic properties. And then sort of finally, sort of more modern day, it's just a Medium post of why, for when it comes to blockchain and smart contracts, why Cardano went with Haskell as a to write sort of the contracts. So instead of using Solidity or some language like that to write the smart contracts, Cardano decided to go with Haskell. And in my opinion, that's quite a good use case for Haskell, where you need to be able to use various techniques and methods to reason about your smart contract and so on. So when it comes to formal methods and proving correctness and so on, it obviously makes a lot of sense to go the Haskell route. Yeah, so in terms of links, that's maybe all I want to provide. So now I'll go back and share my screen. And I'll delete here what I have. And what I'll do is I'll start where I ended last time. And again, I'll define this expression type of mine, and just very simplistic to keep the code short, and then write some evaluator for it. Last time I used the maybe type, and I want to do something slightly different this time. So again, it's sort of just driving home this idea of at least one use case of monads. So again, just trying my best to sort of explain on a very basic elementary level one use case of monads. So what I have this expression type of mine. So either it's a double wrapped inside, so it's a value which is a double, or it's the division of two other expression types. And maybe to make it easy, maybe I should, instead of implementing my own show, let's just derive show. And so then last time we discussed with the maybe type how to evaluate expressions. So again, let's implement the safe diff, and I'm going to do something slightly different and not use the maybe type, but I'm going to use lists this time. So the whole idea is I have two double values, but the y might be 0. And so it's just a question, how should I divide two doubles if the second one might be 0? So so last time I used the maybe type, but let's do something else now. So let's use lists. So it's simply x divided by y, but we assume that y is not equal to 0. So if I just reload this, so if I do a safe diff of 10 and 0, I simply get the empty list. So essentially what I'm using here, so I've used the maybe type quite a bit. So lists are actually a little bit more general than the maybe type, since a list could be empty and that corresponds to nothing of the maybe type. Or it could have a single value. So that corresponds to just 5 or just 10. Or it could have multiple values in the list, which corresponds to having some non-deterministic computation. So now that we have a safe diff, let's now again implement eval, and instead of using the maybe type, I want to use lists. So if I do eval and I have the expression could be either val of a double or it's the division. So we need 2 cases. So val of n. So what I want to do is I don't want to say it's just n. So I want to use the idea of I'll put the value in a list just on its own, if I can. And the nothing situation or division by 0, that will correspond to the empty list. So that's the evaluation of this first situation. Now let's look at the second situation. And we have now an expression with a left side and a right side. So it's precisely division, expression, expression. So let's see how we do this. And obviously that's not expression there. That should be diff. That's why the red underlining helps. So let's use the do notation. And why can we use the do notation? Well, I'll use the fact that lists are in fact monads. So list implement the bind operator. So I'll first write it in this do notation, which is nice and syntactic sugar, so you don't see all the painful detail. So we have this kind of notation. So let's evaluate the left part. So we have evaluate this part, and well, either we get the empty list or we get a list with just the value x in it. So the x corresponds to the case when it's possible to do the evaluation. Otherwise, we don't have an x. And the y we obtain similarly. We just evaluate the right-hand side. So you can think of these x and y's as double values. And then what I can do is I can just say safe diff of x and y. Now, maybe you can't remember, but at least if you go back to the video of last time, this code looks exactly the same as when I implemented with using the maybe type to handle division by 0. So this code looks exactly the same. And that's because whether I use the maybe type or lists, they both monads, and that's why I can essentially write the same code. So let's just try it out. So if we evaluate, for example, the division of val of 10 and val, oops. Sorry, it just got stuck there for a while. Well, val of 0. We simply end up with the empty list. Okay, so yeah, so I thought it was sort of interesting just to sort of have another example of where I use a monad. So instead of the maybe type, in this case, I use the fact the list is a monad, and I just wrote a way to evaluate expressions.
Brink, do
Yes.
you think perhaps you could do a longer expression where you sort of maybe divide twice or 3 times? Twice should be enough, and then you can maybe see how division by 0, you can put it in different places and whether it makes any difference.
So let's see. So if we take some division and perhaps another division, a val of 10 and val of 5 maybe. So yeah, so perhaps that's sort of the left sub-expression, division, val 10, val 5. And the right sub-expression, maybe there we can do something like val of 0. Yeah, maybe I'm not sure if this is complicated enough, but
yeah, that's perfect.
Yeah, maybe not going to see all the details now, but if I now still do a val of e, I'm still just going to get the empty list. And I guess why I almost prefer using lists to the maybe type. If you want the actual value, if the list is, you can check if the list is non-empty, you simply take the head of the list. And that's the actual answer of your evaluation. So you should just check whether you have the empty list or not, and then you just take the head of the list. So it's actually also quite common that many people prefer to avoid the maybe type and they just go with the list type. And rather use that as a monad. Now, something else I want to show you. So let's get some info on monad. And what you see with monads, so what I'm using essentially with the do notation is this bind operator. But in order for something to be a monad, it must be an instance of the applicative type clause. And that's not something I've shown you before. So, so my attempt in the next 15 or fewer minutes, I just want to showcase the applicative type clause to you. And to do that, maybe I'm first gonna, and I'm gonna put it here. I'm first gonna implement, and I'll show you now what it's doing, something I'll call flatten, and I'll use the bind operator here. And let me write it out. And anyone willing to guess what this function, I guess I just need to put the, yeah, there we go. Now the type signature looks okay. Anyone willing to guess what flatten is doing? Anyone brave enough to say in the chat something about flatten? So I'll show you. So the cool thing, so if you look here, so it's just my linter that's smart enough to figure out, well, so what it's doing, so M is a monad. So what I have here in terms of the types, I have a monad wrapped inside a monad, but it just returns type B wrapped inside a single monad. So it's flattening the effect of having a monad wrapped inside a monad. So let me show you, I guess I need to reload. So let's use it. So let's flatten, let's put a list with 2 lists in it. Say maybe 1, 2, 3, and 3, 4, 5. And what it's doing, it's just removing the fact that I have nested lists. So it's just taking all the elements of the list and it's removing the nesting of the lists. And I can use the same code and I can flatten, say, I have something like adjust, but inside the adjust, I have wrap adjust. I'll show you now why I want to use it. So for any monadic type, you know, I sort of get the idea what flattening is doing. And maybe I'll leave it as a little exercise and forcing you to think about this bind operator and what it's doing and how it's implemented for various instances of the monad type class to see this, that this is what's supposed to happen. But let me use this, and I also want to get back to applicative. So instead of using this do notation, I want to use applicative. So to write that code, let me show you at the bottom something we can do with applicative. So say, for example, I have a +2 and this inside, so I have the function +2 that needs one more argument inside a list. And now I use this, I'm not sure what's the right name for this operator, but it's a star inside angle brackets. And that's the operator you need in order for something to be an instance of the applicative type class. And so both lists and maybe that's instances of applicative. So let's now apply to the list 3, 4. And you see it behaves almost like a functor. Essentially, I'm mapping this +2 over the list 3, 4. But notice this function is wrapped inside the list. But I can also do it more complicated, and I can say, well, let's put another function, a ×3 in there. And then what applicative will do is it will take the +2 and apply it to 3 and 4. That's where the 5 and 6 is coming from. And then takes the times and 3, apply it to both those. And let's now take it one step further. I can take, let's just wrap the +2 operator inside a list with the star. And maybe then we just get a list with 2 and 3. And a list with 3 and 4. And essentially it's using the plus, and the first list is supplying one side of the operator. So it's a +2 and a +3, and then I apply those two operators to the 3 and 4. So this whole idea of applicative is, you should think you have sort of a wrapper, whether that's a list wrapper or the maybe type or whatever. And you want to do sort of normal numeric computations without taking the things out of the maybe type or out of the list. And that's where applicative comes in. And now I want to use precisely this idea here. So, well, this is not going to be 100% correct, but let's say we do something like we take division. So that's wrapped inside a list. And we do applicative, and we evaluate the left side, and we evaluate the right side. Whoops. Okay, so, well, at least the type checker is happy with me, but obviously the problem is it could still happen So I could evaluate R and I get a list with the value 0 in it. So that's not quite right. So over here, I should have save diff. And now the compiler is complaining. And let me just show it to you and then I'll explain it to you. That's the reason for this flatten function I showed you guys. So the whole problem is with save diff is it take values and the answer go and sits inside a list. So if I use this applicative style, I'm gonna get a list with lists inside it, or list with a list inside it. And that's why I use flatten. Okay, let me just save it and let's see how this let's see if this is all working. And now let's eval E. Okay, for some reason Zoom and my laptop don't like each other, but hopefully it will, oh, there we go. And we get the empty list. And I guess if I go and change this last value to a 2, just to show I don't always get the empty list, and then I get 0.4. So this is just illustrating this applicative style and how one could use it. And I suppose this is also showing in this very simplistic piece of code, it's not always clear whether you should use the fact that something is a monad or whether you should write applicative style code. So I'm not sure what's the nicest here. Maybe the delimitation and with monads is a little bit nicer, since here I also need the flatten. Okay, let me see. It seems there's a question.
Shall I read the question for everyone?
Yeah, please, Yorick, go ahead and read
Martin
it.
Asks, it's a general question. So typically when he programs and encounters bugs in a program of moderate length, he does a lot of print statements to see what it's doing to find the problem. But under pure functional programming, that would be an impure way to proceed. And he's asking, what are the efficient ways to debug non-simple Haskell programs?
Yeah, so maybe I'm not the right person to answer there. And the small little things I write, I find it convenient just to sort of use GHCI, sort of the interpreter reload, and just add small pieces of code. And sort of the surprising thing, as I've mentioned before with Haskell, if you get away and the type checker is happy, quite often your code is correct. And then something that I can sort of, you get this in all languages, but okay, I'm not going to have time to sort of show you some examples. There's something called quick check that I can recommend. So once the type checker is happy and you just want to make sure sort of the semantically your program is doing what it's supposed to do. You have this way of, instead of writing unit tests, you specify a certain property. And then what will happen is, and you can specify, given this property, generate 1,000 inputs for me that will satisfy certain criteria to verify this property that I claim should hold. So with quick check, initially, if I think it was John Hughes that came up with it when he worked for Boeing, and sort of were looking for bugs in various of their software and so on. So he came up with it in the Haskell setting, and nowadays you have quick check in all languages. So that's something else that I like to use in Haskell for just having a measure of confidence in the small little programs I write. And normally I also force my students to, when they hand in their code, and obviously it's too painful to sort of think whether they've missed something, I force them to write quick check tests. Then I can look at the properties, and then I also feel more confident if I can just verify the quick check properties, see if that's specifying what it should, and then if the quick check is happy with the code, I'm normally happy with it. So yeah, so to really answer that question, I sort of need much more practical experience and than I really do have. But yeah, that in my limited experience, that's the way to go.
Could I perhaps just add, I think one of the big things is a stylistic question, which is that here you'll notice that Brink is often writing a short function, and he can try that out and test it and try it in on the command line, the interpreter, and see if it works, and then build from it to bigger and bigger things. So if you make sure that the small things work, the small components, and then build by composition, then hopefully you have lots of well understood small things and make your big thing out of that. And so the big thing doesn't have a small bug hidden somewhere because you had to redo something in a particular way. You have well-defined functions that do those things.
Yeah, and I think also sort of the classic thing to come back to it, since your functions are pure. A lot of the bugs that more subtle bugs, that's normally due to side effects. You can even see it, say, in languages like, say, Java, where they try and force you, or they try and make sure you don't have some of those bugs by making certain types immutable. For example, in Java, your strings are immutable, and that's just to avoid all kinds of subtle bugs that's due to side effects that you might get if you work with strings. But yeah, in general, all your functions must be pure, and you sort of have to work in impurity or hide your impurity in monads. That's another reason why a lot of the bugs that you would have had in when you used other languages simply will not appear here if your small components are sort of correct. So yeah, so I have more stuff prepared, but yeah, I see it's 3 o'clock, so maybe it's a good place to stop. And yeah, I guess also I had a brief discussion before we started with Yorick. Yeah, so obviously all my code, it was just in main.hs or lib.hs. So obviously if you write proper code, a little bit more code, you'll do the proper modular things and put functions that belong together in their own module, and sort of package that module and just do imports of when you sort of build things from these various modules that you have. So something I didn't show, but that's sort of fairly easy to handle. Yeah, so I also, the other thing I mentioned to Yorick is I sort of, apart from giving you some links, I felt exactly not sure how to sort of end everything off on so that people feel this is a high note or a bang or whatever. It's just stopping somewhere in the middle, but at least I feel now you should have a feeling for monads, at least for lists and the maybe type, which is often the first stumbling block that people encounter when they play around with Haskell.
I think one of the obvious things is we can collect everything that we've done and just put it somewhere that people can download it and play with it a bit. So
yeah,
I
good
think
idea.
the high note should continue forward if there's one.
Yeah, and as I said, I can really sort of recommend Graham Hutton's, well, no, it's easy lazy, that you just watch the videos, and yeah, once you're done with those 2 courses, yeah, you'll be a pretty decent Haskell programmer, and well, that's more or less my level, where I understand everything he does in his two courses. That's more or less my level of Haskell skills.
Okay. No, thank you very much. And yes, I will add these resources to the YouTube page, because I think I already mentioned in the page from the Nottingham University, but I will add the other links as well. And the only thing, because I don't see, do we have any more questions? Because we have a note of thanks in the chat, but there is no more questions in Q&A. And yeah, so kind of what I can say, I can just thank you on behalf of the NITheCS for delivering this very nice mini school. And I hope that we all could learn a little bit of Haskell. And I hope that this discussion of the kind of mathematical aspects and more computational computer science aspects of the category theory will continue. And as you know, that there will be no mini school in December, but there will be new mini schools in 2022. But NITheCS will still do seminars, and there will be a seminar next Monday, and some of you probably already got an announcement. Okay, thank you very much. Thank you.
Thank you.
Pleasure. Thank you. Thanks a lot for the invitation.
Yeah, thank you. Bye-bye.